So to briefly recap on what we did the last time before the exam. So we were looking at surface integrals, and then we got to a special kind of integral called a flux integral, which essentially measures the rate of change of some fluid across a membrane, if you will, across a screen. And that screen, of course, is going to be given in the form of a surface, which is a function of two variables. All right, so that's what a flux integral is. Well, how do we distinguish flux integrals from the regular surface integrals? Because number one, the first case of a what's it called of a surface integral. Let me go all the way to the beginning just to wrap up, so to speak, just to summarize what we had. So we had the simplest surface integral. Number one, the surface integral will have a ds. It's not a dA or a dB. And that ds will be the element of surface area, which we went through all the details where it came from. That is that little piece of skin of a surface that we find its area, and then we turn it into infinitely many of those, Riemann sums, right? All the story about Riemann. That's number one. Number two, then there's the most generalized kind of surface integral, where the integrand, it's no longer a number one, it's a function f of x, y, z, where that function, f of x, y, z, well, for the sake of simplicity, we would think of this integral as finding the mass of that shell given by the surface. And well, that function f of x, y, z, it represents actually the density of the thin layer of the sheet, if you will. All right. Now there's a little catch here, because this is a double integral. Remember, this is a double integral, and that density function, which is a three-variable function, how we need to. This is weird, because a double integral, which is either dy dx or dx dy, what is that? That is, we have a problem when it comes to defining the integrand, because we need to get rid of one of the variables here, right? So one of those variables, what is that? Z or x or y, depending on whether we're projecting onto the xy plane, onto the yz plane, or the xz plane. We did a couple of examples. We did one example in which we were still sticking to projecting the xy plane. All right. Actually, that was the easiest case. However, we were playing with the points of view right here. Now we project it onto the YZ plane, and yes, in a way, we make the problem a little bit more complicated. But that's so. The purpose of this exercise was so you can see how do we do the projection onto another plane, and also if we need to get rid of one of those variables. In this case, since we were projecting onto the YZ plane, that means our differential dA for the surface integral is going to be dz dy. That means the x variable needs to be taken away. How? You know the drill here is by using the original function. However, that function would be a function whose dependent variable is x, and the independent variables are the ones involved in the differential y and z. All right. So we did one example, and then we did one, applied to finding the mass of this funnel. Yeah, we had fun with that one, and then we went to describe these flux integrals. All right. So we did one example. Let's go back to this example. So, well, again, now how do we distinguish? That was the question, the initial question. Well, the first surface integral for the area of the upper surface and the mass of the sheet. Both of those integrals do not involve a vector field like in this case the flux integral. Well, again, that's because we need to think of the physics behind flux. So some fluid is not going to flow by itself, right? I mean, it may be at rest, and in that situation, the flux will be zero, which is fine. So in order for a fluid to flow and go across a screen of any shape, there's a driving force required. What is that driving force? The vector field, right? That's the driving force. So this flux integral, it's calculating the flux across the paraboloid and also across the bottom, the circular bottom. So actually we needed to split this problem into two parts. So that's the driving force across the surface given by those equations. Okay, so what did we do? So we plotted the region, the solid, where we were going to find this flux, and we got halfway through setting up the double integral that calculates the flux across the part of the paraboloid. So we got to this point where we expanded, where we got rid of the z to get an integral in terms of x and y. So here we go. Let's simplify this integral, combine like terms. It seems like we have x squared, y squared, x squared, y squared. Let's simplify. That's the integral. I'm not going to iterate yet. I know what you might be thinking, the circular region, but hold on. We'll do that in a second. So still over the region, not over the surface S anymore. That's over the region R, if we will, because we are already iterating, right? Over the region R. So that'll be x squared plus a y squared plus 2xy plus 16. Okay? dA. We'll talk about the limits of integration in a second. Now, think about it. No GeoGebra at all for this one. Hopefully by now, you guys can use your imagination and see what's going on in the projection onto the XY plane for the surface. So, don't think about the 3D space for now. Think of the XY plane. What's the projection onto the XY plane? Anybody? Loud. Don't do pictures on the air. Loud.
It's a circle.
It's a circle, right? It's a circle of radius. What's the radius of this circle, by the way? 4? Okay. Well, how do we get that? Well, we haven't. Oh, to do that, we need to set these two surfaces equal to one another. That is, okay. Let me use a different color for this. That is 16 minus x squared minus y squared equal to 0. That means x squared plus y squared equals to 16. Yes, that indeed represents the circle of radius 4, which is the circle right here, which is the floor of the solid, right? Okay. And because we have a double integral, and we're also integrating this over a circular planar region, do you feel like integrating with these crazy radicals? Do you feel like doing that? Or what would you do in this case? What would you do? Polar coordinates, right? Polar coordinates, yes. Not cylindrical. Be careful. Cylindrical is for a triple because oftentimes we get to confuse them because, I mean, they look the same. Well, the only difference is the z, but that's in the case where we have a triple integral. All right? Okay, so substitutions. Let's do the substitutions for the polar coordinates. That is r squared, all these two terms. What is x? That's r cosine theta. That is r sine theta. And 16 is just 16. All right? Okay. So what is this? Let's substitute the new coordinates. So x squared plus y squared, that equals to r squared plus 2 times r cosine theta, r sine theta plus 16. R dr d theta, and we are integrating between, okay, let me make some space here, I'm gonna need it, okay, there you go, We're integrating for a radius between 0 and 4 and between 0 and 2 pi for the angle. How do we know it's between 0 and 2 pi for the angle? Well, in the problem, they're not telling us any additional conditions such as find the flux across only in the first octane. Actually, if it were even only in the first octane, we would be running into a harder problem. Then we would have to evaluate, what is that? Four flux integrals, and well, that's actually something we're gonna do later. All right, well, ish. So, well, I don't want to evaluate this double integral. I'm just gonna give you the result. I think you guys can integrate r squared. You can integrate the product between cosine and sine. That's a pretty basic use of, and integrate 16. So the result for this will be 384 pi. All right, so that is the flux across the paraboloid part. All right, now let's do the second part of the problem. That is the flux across the bottom. Because why are we? What are we doing? So we are solving a piecewise smooth surface. Because if you look at the intersection between the paraboloid and the bottom, it's not smooth. It's sharp. So we need to split the problem in two parts. In a similar way, for the line integrals, that we calculate the work done for a piecewise function when we have this sharp corner. Remember those triangles? We had to use 3 line integrals. Well, later we'll learn about the fundamental theorem of line integrals, and we did that in a quicker way, even better with Green's theorem with the double integral. All right? Okay, so number 2. So something similar we're doing here with these flux integrals. So number 2, across the circular bottom. Okay, so number 1, what is the surface that describes the circular bottom? Any ideas? The surface that describes the circular bottom. Let me go back a little bit to the top. Which of those surfaces is? That's part of the paraboloid, so the square root. So I mean, think of that circle. Where is that circle on? X and Y, and it's on the XY plane, right? But out of these two surfaces, which one describes the bottom part of the z equals 0, right? So that's z equals to 0. So for z equals to 0, okay, so we need to find the partial derivatives of the surface z equals to 0 with respect to x. Oh, easy, 0. Partial of z with respect to y. Oh, easy, 0, right? So that's going to simplify our integral a lot. Okay, so the double integral of the surface S of f dotted with big N, the big S, that is the double integral of f, but what's f? F, it's the same vector field, that is x plus y, comma, 0 in this case. Okay, what am I writing this 0? Because do you see this z right here? In this case, z equals to 0. In the previous part, the previous case, we replaced the z right here with the function here later on, right? Okay, so that dotted with nds, which is in this case simply that negative partial with respect x, negative partial with respect c, and 1. But what are the partial derivatives? Aren't they 0 and 0? So, comma 1, the 1 by default, dA over the region R at this time, because we're already about to integrate. The ds now becomes dA, s becomes R, the planar region of integration. Okay, so dot product x plus y times 0, isn't that 0? Y times 0, isn't that 0? 0 times 1, isn't that another 0? So, what's the double integral over the region R of 0 dA? 0. So there's no flux across the bottom, the circular bottom. So the total flux, would that be total flux, that is the flux about the flux across the paraboloid, which is 384 pi, plus the flux across the circular bottom, which is 0. That's simply 384. All right, that's about it. Okay.